Thank you, Professor Xie. It's my great pleasure to come to Hong Kong to celebrate the 10th year anniversary of the Future Science Prize. I was asked to talk about the chemistry recently achieved in my lab. In the Shanghai celebration event, I talk about the hydrogenation reaction. Today, I would like to talk about the largely hydrogen bond insertions, because my field is asymmetric catalysis that deal with the chiral molecules. But actually, we know that chiralities is widely exist in nature in different metal levels. Actually, in all levels of the metals, you have the chiralities. Bigger like the labular, small like the DNA molecules. In all levels, actually, you have chiralities. But for the chemistry, we are mostly interested for the molecular levels of the chiralities. Why? Because the chiral molecules have two different enantiomers, and those two different enantiomers have different properties, mostly have different bioactivities. For example, the aspartame. Now we eat that every day in your coffee, in some sugar, some ice. You have this aspartame as the sweeteners, because almost all us like sweeter. But if you eat much sugars, you will get a problem. But this aspartame, this molecules is peptide, is healthy, but it gives you much sweeter tastings. It's almost 200 times sweeter than the sugar. But another example is not present. It's a disaster. In former time, we didn't know the enantiomers of the chiral molecules have different properties. And we use, actually the pregnant women use this thalidomide to treat the pregnant reactions for the pregnant women. Actually, this molecules has two enantiomers. One is the sedatives, is the hair of the woman. But another one can cause fetal malformations, because we didn't know that. In that time, we used a mixture of these two enantiomers, so it gave us a disaster. And after that, the FDA or most that agency in different countries had the rules for the chiral drugs. You must use one enantiomer. That is the medicines. You cannot use the mixture of these two enantiomers. So now in the marketing medicines, you have more than half of them are chiral enantiomers, chiral molecules in the optical enantiomers. And in the developing medicines, you have more than 70. Other 30% mostly are achiral, without chiralities. Or these examples of the chiral medicines we use. For the synthetic chemist, we need to develop the method to making these chiral molecules in the enantiomerically pure form. That means how we can make just one isomers without other isomers. Those are methods we use to prepare it. You can use the racemic compounds, use a mixture of these two enantiomers to isolate one. We call it the chiral resolution, or you can do some asymmetric synthesis, starting from a chiral molecule to make chiral molecule in enantiomeric pure form. That means you make one enantiomer without other enantiomers. If you use catalytic amount of the reagent, that means you are doing asymmetric catalysis. Of course, you can use the artificial catalyst. You also can use enzyme. That's a biocatalyst. Because in this asymmetric catalysis, you only use a small amount of the chiral catalyst. You can make a large amount of the chiral product. So there is the asymmetric amplification in this process. This is why in last few decades, this area developed very fast. Many chiral catalysts has been developed. And we developed one type of the chiral catalyst, lambda spiral catalyst, with these core structures. This is spiral by indent structures. With these structures, now we can make large amount ligand. With this ligand plus different metals, we can make almost unlimited number of the chiral catalysts. Actually, the spiral catalysts have been employed in over 70 or 700 asymmetric reactions. And in my lab, we have done this many reactions, including carbon-hydrogen bond formations, carbon-carbon bond formations, and carbon-hydrogen bond or hetero-atom bond formation reactions. Today, I just talk about one reaction, is the nitrogen-hydrogen bond insertion. And in this hydrogen bond insertions, actually, it's a carbene insertions. We know the carbene is the intermediate in the organic synthesis. But the free carbene is too active. Too active means no selections. If some reactions have no selections, there's useless in the organic synthesis, because in the organic synthesis, you must do some selective reaction. But free carbene is too active, is less selective, has less application in the organic synthesis, but later on, the metal carbene was developed, but the metal carbene still active, but not that active as the free carbene. So it has some selections in the organic synthesis. So metal carbene have been applied, have been used in the organic synthesis in last few decades. Of course, you have the two types of carbene, Fischer or the Schrock carbene. But in the asymmetric catalysis, using carbene intermediate, and many reactions have been developed, and many scientists have achieved great success in these areas. But reactions like the cyclopropionations and the cyclopropionations and elite reactions, or the carbon-hydrogen bond insertions. In all these reactions, they achieved very high initial selectivities. But we are interested in the carbene insertion to the heteroatom hydrogen bond, to making carbon heteroatom bond. Of course, with the initial selectivities. So we are interested in the reactions of insertion to the nitrogen hydrogen bond, oxygen hydrogen bond, sulfur hydrogen bond, or boron hydrogen bond, many heteroatom hydrogen bond insertions. Today, just talk about the nitrogen hydrogen bond insertions. But before us, some lab already tried these reactions. For example, McCurry used the dirodium catalyst to catalyze intramolecules nitrogen hydrogen bond insertions. He achieved about 50% yield and less than 50% initial selectivity, EE value. Jorgensen used the carbon complex with the dioxazole ligand to do the intermolecules nitrogen hydrogen bond insertion reactions. He achieved also around 50% EEs. And when we developed spiral bisoxazole ligand, we want to try these reactions. In the beginning, we used the copper halide, chloride, and some neutral carbon precursors. We did achieve the very low initial selectivities, as the other people got. But when we try the ionic carbon precursors, and we found these reactions can give us a high initial selectivity, of course, with the spiral catalyst. The best results was achieved with these very bulky anions. This means this reaction needs very bulky anion, very weak coordinating anions. This is why the Prof gave us best results. Of course, we screen lots of the carbon precursors, but finally we found this one is the best for these reactions. Of course, we studied a different type of the spiral ligand with different chiralities, because in this spiral bisoxazole ligand we have 3 chiralities, so we must study the combination of these 3 chiralities. The combination of the chiralities SSS is the choice of the catalyst. And in the beginning, the review always asks us to make a comparison with other type of oxazole ligand, but we did. And the bisoxazole ligand with these bilepsal structures or the Evans bisoxazole give us much lower initial selectivities. Of course, a different type of the aromatic amines can be used in these reactions. And Professor Greg Fu and Xiaoming Feng also did the reactions afterwards by using the copper catalyst. They achieved high initial selectivities also, especially the Greg Fu can use this amide. This gives us advantage because this amide can be deprotected after reactions, getting or obtain the amino esters with the free amino groups. And we studied the structures of the catalysts because almost all the chemists believe the properties come from the structures of the catalyst. In other words, the structures determine the properties of the molecules. So we studied the structure of the catalyst. We try hard to make a single crystal of this catalyst. We spent a few years. Finally, we got the crystal. And we found this catalyst very special. It's different from other type of the catalyst because other copper complex used in this carbene transformation, there always is the complex of the one copper and one ligand. And our catalyst is the two copper and the two ligands. And coordinated in this symmetric patterns. And if we take the one part and then look at if the reactor with the precursors of the carbene and generate this copper carbene, and then give us this product. So now we understand these reactions happens from these models. And you may ask, your catalyst is a dimer. That means the stable catalyst is a dimer. Is the active catalyst in the reaction cycle, catalytic cycle, is still a dimer? We check this nonlinear effect. We found there is a nonlinear effect in this reaction. This means the active catalyst still contains two ligands. Otherwise, it will not give us nonlinear effect. And we also check the catalyst by mass in the reaction solutions. That show us the catalyst still dimer there. And we also did the kinetic study of this reaction. We found this reaction is the first order for the catalyst, the zero order for the diazole and the adenine substrate. And this is the mechanism we proposed. The first step is the generation of the metal carbene, and then the attack of the adenine to this electron deficient carbon of the carbene, generate this metal associated elite. And if the proton migration happens at the same time, the chiral catalyst leave. If these two processes happen at the same time, and we can get the chiral product in high initial selectivity. If the catalyst part leave before the proton migration step, we cannot get initial selectivity. So because we got high initial selectivity, so we believe our reaction happens through this process. And now many subjects cannot give us a high initial selectivity. Let's show us probably they go through this way. It goes this way. And the question is, if the reaction goes through this way, can we control the initial selectivity? And we think about that. We thought if we can control the initial selectivity in the proton migration step, probably we can control the initial selectivity in this way. We don't need use the chiral catalyst to control the first step, but we can use the chiral catalyst to control the next step. If we can do that, we can use many types of the other subjects. As I mentioned in the beginnings, if I use the carbon complex of the spiral, because oxazole, we cannot use the amide as the grateful used. But if we can do this way, we can control the initial selectivity in the second step, probably we can use the amide or other type of the substrate. So we try this reaction. The first, we use the achiral rhodium catalyst to generate the metal carbene. This step, we don't need to control the initial selectivity. But the second step, we use the spiral phosphoric acid to control the initial selectivity of the proton migration step. And after a modification of this spiral phosphoric acid, we finally can control the initial selectivity. But this E levels is not very high. And after modification of the A chiral of the dirodium catalyst, we can increase the initial selectivity to the 92%. But interesting, we already know this dirodium catalyst A chiral, it should not give us influence for the controlling of the initial selectivity. Why? With a different group, it gives us big improvement for the increased initial selectivity. That's interesting. Because we use the two catalysts, one is A chiral, one is the chiral. So we have to use, study the ratio of these two catalysts. We can use more phosphoric acid catalyst. We cannot use more dirodium catalyst. If we use more dirodium catalyst, it generates the metal carbene too fast, and that one can go the proton migration step without chiral phosphoric acid. So we must use a little bit more phosphoric acid catalyst. And asked by the reviews, we also make comparison with the bilateral phosphoric acids that give us a much lower initial selectivity. Of course, different diazo compounds that carbene precursors can be used in these reactions. And this is a mechanism we proposed. And with this mechanism, now we can understand why different A chiral catalysts still give some influence to the controlling initial selectivities, because in this step, this dirodium part is still there. So this is the reason why we need a very bulky dirodium A chiral catalyst. Of course, this is normal kinetic cycles for these carbene insertion reactions. With this two methods, we already solved the nitrogen hydrogen bond insertion with aromatic amines amide. But now the question is, how about the aliphatic amines? Because we have much more the aliphatic amines compare aromatic amines and amide. But the question is, this aliphatic amines is more basic, is more nucleophilic, and it may destroy our catalyst. You see, if this aliphatic amine used, it could destroy our catalyst and give this free elite. But can we control this step? Probably. So we try. And now we cannot use the dirodium catalyst because the dirodium A chiral catalyst can be destroyed by the aliphatic amines. And we cannot use a normal carbo complex, A chiral complex, because it also can be destroyed by the aliphatic amines. But finally, we found those very bulky tridended ligand can protect the carbon catalyst from the attack of the aliphatic amines. You see, if we use that, oh, cannot use, see the last lines, and with that we can achieve the reaction we want. But we didn't use the A chiral, we did not use the chiral catalyst to control the next step. And now we need to study which chiral catalyst can use for this reaction. You see, this time the spiral phosphoric acids or other type of the catalyst for the proton migration step cannot be used. You see, all of them give us either racemic or the very low EEs. Only this chiral, this Sia union can give us about 50% EEs. And then we try different type of the precursors, and with the bulky acid group, and we can achieve much higher initial selectivity. And then now we found with this very bulky copper achiral catalyst plus chiral Sia we can get a high EE. And then we study different chiral Sia catalysts, we can increase the EE to the 90%. And now we can use different type of the aliphatic amine to do these reactions. Okay, this is subject scope. It's a different type of the precursors we can use, different type of aliphatic amine we can use. And why this can work? Please remind me if time is. I didn't see the time in there. 2 minutes. Oh, sorry. You see, in this NMR structure show us that ligand can protect this carbon from the attack of this amine. Aiding this one, the NMR, this proton has now changed. If I aiding this one, and this proton has shift. This means this ligand can coordinate to these carbons, and aliphatic amine cannot coordinate. This coordination of the Sia to the carbon is very important. That's the secret for the reaction success. You see, the pKa of this catalyst increased very much by coordination of this Sia. You see, and the acidity of this one increased. So this is why this catalyst can catalyze the proton migration of these reactions. Okay, this is the mechanism drawn by Jacobson. As he said, this catalytic 1-2 punch is with this coordination of these Sia and this, with this one, is increase this acidity of this, and then helps this proton migrations and generate this product. So I think I cannot talk another stories because the time limitations. And actually, after this aliphatic amines, we think about can we use ammonia? Because it's ammonia, it's much difficult to control the initial selectivity of the reactions in many reactions. But in these reactions, finally, so as through quickly. Finally, we found with this catalyst, and we can increase the acidity of this even higher. You see, with this increase of the acidities, we can solve the problem in the ammonia nitrogen-hydrogen bond insertion reactions. So I go quickly. Okay. Oh yeah, I just go through. So with almost 18 years effort, finally we solve the nitrogen-hydrogen bond insertion for all the amines, aromatic, aliphatic, amide, and ammonia. Finally, I want to thank my colleagues and students for their creative work, and also would like to thank those funding agency for the support. And thank you.